Hello guys, welcome back to another video. In this lesson, we are going to cover collision theory and the four factors that affect the rate of reaction. So let's go back first and go and talk about chemical changes. So this is something that we have covered in previous lessons. Whenever we talked about chemical changes, we specifically were talking about reactions that result in bonds being broken and or formed. So whatever substance, whatever element, compound it is that we start with becomes rearranged. So some of those bonds break, some of those bonds form, and we end up with new products. So if you need a refresher on the different types of chemical reactions, we do have all those lessons already posted in our channel. So let's talk about collision theory. So again, we're going to be talking about specifically chemical changes. So what needs to happen? There's this theory called collision theory that basically states that in order for bonds to be made or broken during a chemical reaction, some things need to happen first. Reactants have to collide, and they just don't have to collide, meaning they have to touch in a way, they have to interact. But they also need to interact with enough energy and in the correct orientation. And that goes back to polarity. So when we talk about collision theory, we're talking about not just collisions, we're also talking about sufficient energy and correct orientation. So, and again, in other words, the atoms, the ions, the molecules, they first need to collide. When they do collide, they need to collide in the proper orientation, so in the right way. And they also must collide with enough energy for those bonds to be broken and remade. So let's look at some examples. So here on the left, we have two football players, right? And while probably the one that is trying to tackle the other Texas A&M outfit, he did it in the right orientation, and he did collide with him because you can see the hand that was touching, but he didn't do so with the right amount of energy. So we don't have a successful tackling. Now on the second one on the right, we do see the three things happening. We see the collision, we see the right orientation, and we also see the correct amount of energy. So this is just kind of like a silly example of how collision theory does apply. And think about this example whenever we're talking about particles colliding, interacting with each other in order to form or break bonds. So here in this example, we have the correct orientation and the sufficient energy. So therefore, we have different new products. So here we can see that we have a successful chemical reaction. In this example, we don't have the correct orientation. We do have enough energy. So just because we have enough energy to make a collision take place, if the orientation is not correct, we don't get a reaction. So our reactants do not form new products, so therefore no chemical reaction. On this last example, we have correct orientation, but the amount of energy is not sufficient, and therefore we result with no reaction. So we have to have all three things. As a recap, we've got to have collisions, we have to have enough energy, which we call activation energy, and we have to have the proper orientation. So now that we talked about what are the three things that need to happen for bonds to be broken or formed, we also need to talk about, within collision theory, what is going to help us speed up, or in some cases, slow down the rate of reaction. And when I talk about rate of reaction, I'm talking about how fast or how slow a chemical reaction is taking place. So there are four main things that we can talk about. The first is going to be surface area. And this is by far the one that gives students the most trouble because we don't have a good understanding of what surface area means and what its relationship with reaction rate is. So here on screen, we have the definition. Surface area is going to measure how much exposed area a solid object has. So think about like in terms of size of your reactant. So let's do something simple. Let's talk about sugar. We know that sugar comes in sugar cubes, right? So we got the little cube, and it has a pretty low surface area because let's say that we wanted to take a sugar cube and we wanted to dissolve it in some sweet tea that is, hot and getting ready prepared. So if we were to do that, in order for the entire sugar cube to be completely dissolved, it would have to be dissolved layer by layer. So first the outside, and then the middle part, and then eventually we would get to the middle part of the sugar until the whole thing would be dissolved completely, right? Well, how then would the surface area be affected? So let's say that we wanted to increase the surface area, meaning we are not, and this is where students get confused. When we increase the surface area, we actually make the sample smaller. Think about it. If we were to take that exact same sugar cube and we were to crush it down into, the small, tiny little granules that we see that most of us associate with sugar, right? We would have a lot. What has more exposure to interaction, to form those collisions that we started to talk about in the video? Well, think about it again. We have a sugar cube with low surface area because the only thing that is exposed is the outside of the cube versus the exact same quantity but in granule form, so like the one that we already crushed down. Well, the one that we would be able to dissolve a lot faster would be the one that is in granules because it's already smaller, right? Smaller pieces, and all of them at the same time would have that interaction, those collisions with the sweet tea of the example. So when we talk about surface area, when we increase the surface area, right, meaning we make the solid or the sample smaller in size, then the reaction rate increases. And always go back to that example of the sugar cube and the sugar granules. What's going to be faster, right, easier to dissolve? The smaller the particles, right, the smaller the size, the greater the surface area. So if the surface area increases, right, then the reaction rate also goes up and vice versa. So we have surface area with a direct relationship. So I'm going to do direct here on the side. And again, increasing surface area means making something smaller in size. Now let's talk about temperature. This is something that a lot of us can relate to. We know that when we heat things up, reactions happen faster, right? You've experienced it in many, many aspects of your life. I'm sure you have seen it at some point in the kitchen, right? So just as a recap, temperature is the average kinetic energy. And as we increase the reaction rate, that would mean that we would have a temperature increase. So temperature goes up, reaction rate goes up. So here we also have a direct relationship. And of course, it's assuming that we're not messing up with the pressure. Okay, let's move on. We also have concentration. So when we talk about concentration, we talk about the quantitative measure of the amount of solute in a given amount of solvent or solution. So think about, for example, some acid and some water. The more water you have, right, in a sample, in comparison to how much acid there is, the concentration would be different. So let's just say that we were to take a beaker and we would fill it up with this much acid, and the rest of it would be water, so H2O. Let's say that we were to take a beaker of the same size. We would fill up this much with acid and just a little bit of H2O. Well, which one of the two would give you more reaction, right? So think about what we're talking about here, the acid. Well, the one that has the most acid is going to give you the greater reaction. So here we also see the same relationship. As the rate of reaction would increase as we have more of a concentration. So we would have also a direct relationship. Now, for a catalyst, that is something that we quite haven't discussed, but we're getting introduced to now, and we'll discuss further in the next video. But a catalyst is a substance that increases the rate of reaction without itself being consumed in a reaction. We have done a few labs in the class, and you guys who are my virtual students, you have seen the catalyst being used in some of the labs that we did during the reaction rates unit. So these are the compounds usually that we add to a particular setup that helps us speed up the process of of whatever it is a reaction we're trying to create. Now, we don't usually take them into consideration when we write the chemical equations because they're not part of the chemical equation. They're just there to speed it up. But here we also see the same relationship. So when we have more catalyst, or as a fact, we just add catalyst, we would have an increase in the reaction rate. Now, I do want to go back one more time to surface area because I know that this is the one that students have the most trouble with. So when we talk about surface area, remember, we increase the surface area by decreasing the size. So if you want to think about maybe surface area, so SA for surface area, and the size, so those would be different. Those would be an inverse relationship. As the surface area goes up, the size of our sample, the individual sizes, right now, I'm not talking about like the total quantity, but the size of it would go down. So then, therefore, the surface area, as it goes up, then we would have an increase in the reaction rate. Just make sure that before you leave this video, you go back and double check your information for surface area. This is the one, like I said, that can see most trouble with students. So the main idea for this unit is that we're going to be talking about enthalpy. And we'll define all of those terms later, but also remember, we have endothermic, exothermic processes. We've been talking about these for quite some time. We have talked about endothermic, heat being added to a system. And right now, all we need to know for this particular lesson is that a change in enthalpy that represents endothermic would have positive amount of energy. So whatever energy we started with and whatever energy we end with, we're going to end up with more than what we started with, okay? Now, for an exothermic reaction, our enthalpy change, so remember, energy being removed, is going to be negative. So at some point in the reaction, we lost energy. So lots of things that we have covered. We have talked about what needs to happen for a collision to take place. We have talked about how we can speed up or slow down reaction rates. And we have now just kind of made a bridge and a connection between endothermic reactions and exothermic reactions with enthalpy. So we are going to now look at the energy diagram. And this is, once again, another graph that we're going to be looking at and kind of analyzing what's going on. So in a graph like this, energy diagrams, sometimes they're called potential energy graphs. So you'll hear me talk about both. We're going to look at time and potential energy. So at the beginning of a reaction, the potential energy, so nothing's really happening, right? So we have no change in the potential energy. So our reactants are just there. With whatever energy they have, they're just there. Eventually, though, we would need to have some form of energy input. So that's a big misconception a lot of students have. They think that because something is endothermic or exothermic, the heat only entered or only left. Well, we're talking about the overall, because in any given reaction, you will always need to have some sort of energy being put into play. So for an energy diagram, we start with the reactants at time 0 or close to time 0. Eventually, you will add energy, and that change in energy right here, that we called the activation energy. And this is the one that we were talking about at the very beginning of the video, that we talked about needing energy, right? The sufficient energy during a collision for a reaction to take place. If you do not meet the activation energy threshold and reach the activated complex, so activated complex, if we don't reach the activated complex, there won't be a reaction, right? And we will eventually learn how much energy we need for the activation complex to be reached. But for right now, we just need to know where it falls in the graph. Once we have our reactants with enough energy, then a reaction starts to take place. Of course, assuming that the particles are they're interacting in the right orientation. So the reaction takes place, it's taking place, and eventually, not always, but it depends if it's endothermic or exothermic, we would end up with our products. And those products might end up being end up releasing energy or absorbing more energy. And that absorption or release of energy has to do with how much energy is required to form bonds or to break them. So when we talk about the change in enthalpy, so is this endothermic or is this exothermic? We have to look at the difference. If our reactants are higher than our products, then, right, we are going to have, actually, let me explain it a different way. We always want to do products minus the reactants, because you will always be given some sort of value for the potential energy. Now, if the products, if we have a lower, so in this example right here on screen, our products are, I'm just going to make up numbers. Our products ended up at 10 and our reactant started at 20. Well, we would do 10 minus 20, right? So 10 minus 20, that would give us negative 10. So that tells us then that this is an exothermic reaction. We released energy. We started with 20 for the reactants of energy. We added energy for the activated complex. And eventually we lost a lot of that energy because we had to use some of that energy that we added to form new products, new bonds. And we ended up with only 10. So the change between the two was negative 10. Okay, so this is an example of an exothermic reaction. Now you're going to have to imagine this one because I don't have it as a visual. But if we had a higher value for the products, let's say that, I'm going to change colors here, I'll do blue. Let's say that we started with the same reactants, we increase our activated energy, right? And then eventually we ended up here where the blue line is for the new products. Well, that right there is barely above the value that we started with. So for this blue made up color that I just created here, let's say that we ended up with 25. So we would do the product at 25 minus a reactant that started at 20. We end up with the difference of 5. Because that number is positive and because visually we can see that the products are higher than the reactants, then we can safely assume that this blue graph, whatever reaction it represents, is an endothermic reaction. So for better visuals, here on screen you have the endothermic and exothermic generic version of the energy diagram. So what we have here on the left is our reactants starting at a lower amount of energy than our products. And because then there was a total gain of energy, that would represent the energy that is absorbed throughout the reaction. Now on the right side of the screen, you have your exothermic reaction. So for our reactants, we are going to have a higher value when compared to the products. And that change in energy is the energy that was released during the chemical reaction. In our next video, we will cover the information of heating curves and specifically how we calculate some of these, or how do we visually represent some different scenarios. Thank you all guys for watching.